All right, let's talk about the ideal gas law. It sounds kind of epic, right? One equation to rule them all, and you know what? It pretty much is. Today, we're going to break down this single, powerful equation that governs the entire invisible world of gases all around us. Let's get into it.
It all kicks off with a really simple, everyday question. You've definitely seen this warning label, maybe on a can of hairspray or spray paint. Contents under pressure, do not incinerate. It feels like common sense, sure, but what's the actual science going on here? Why is heating up a sealed can such a terrible idea?
The answer isn't just because it'll explode. It's about a set of really elegant mathematical relationships between the pressure, the volume, the temperature, and the amount of a gas. By the end of this, you won't just understand the warning label, you'll see how we can calculate exactly how dangerous it can get.
Okay, before we can get to the master equation, we need to understand its parts. Think of them as the individual instruments in an orchestra, each playing its own simple tune. We'll start with the one that solves the mystery of our hairspray can.
This is Amundsen's law. It describes a really direct relationship. If you hold the volume of a gas constant, like inside that sealed metal can, and you crank up the heat, the pressure inside is also going to climb. It makes total sense, right? Heat makes those gas molecules zip around faster and faster, slamming into the walls of the can harder and more often.
So, the crucial point here is that for this law to work, two things have to stay the same: the volume of the container and the amount of gas you've packed in there. When those two are locked in, pressure and temperature are basically holding hands, marching up and down together. And remember this, it's super important. For all the gas laws, temperature must be in Kelvin.
Next up is Charles's law. I bet you've seen this one in action. Have you ever taken a balloon outside on a really cold day and seen it kind of shrink and look all sad? Then you bring it back inside where it's warm and it plumps right back up? That's it. That's Charles's law. It shows that when pressure is constant, the volume of a gas and its temperature go up and down together.
And again, notice the constants. For Charles's law to be in effect, the pressure and the amount of gas have to stay put. Colder gas molecules are just moving slower, they huddle together a bit, and they take up less space. Warmer ones get more energetic, spread out, and boom, the volume increases.
Now for something different, an inverse relationship, Boyle's law. This one is super intuitive. Imagine you have a syringe, and you put your finger over the end to trap the air. As you push the plunger in, you're decreasing the volume, and you can literally feel the pressure of that trapped air pushing back, right? It's increasing. So more space means less pressure. Less space means a whole lot more pressure.
So, Boyle's law works its magic when the temperature and the amount of gas are held steady. Unlike the first two laws we saw, this one's like a seesaw. As one variable goes up, the other goes down. This whole idea of inverse proportionality is a really key piece of the final puzzle we're building.
And our final simple law is Avogadro's. Honestly, this is the most straightforward one of them all. If you keep the temperature and pressure the same, and you add more gas to something flexible like a balloon, what happens? It gets bigger. Its volume increases. More gas simply takes up more space.
So putting it formally, Avogadro's law says that volume is directly proportional to the number of moles, and moles is just our chemical unit for the amount of something. So long as pressure and temperature don't change, more moles equals more volume. Simple as that.
Okay, so we've got four separate, simple relationships. Each one is really useful on its own, but what happens when everything is changing at once? What we really need is a way to bring them all together. And this is where the real magic happens.
So check out how we can stitch this all together. You'll notice volume is kind of central here. It's directly related to temperature and the amount of gas, but it's inversely related to pressure. So when you merge all three of those relationships, you get this, the ideal gas law. PV equals nRT. This is the one. This is the master equation. It just so elegantly connects all four of those properties, pressure, volume, amount, and temperature, into one single powerful statement.
So let's break it down real quick. P is pressure. Usually we use atmospheres. V is volume, in liters. Little n is the amount of gas in moles. T is temperature, and you know the rule, always in Kelvin. And what about that big R? Well, R is the ideal gas constant. Think of it as the magic number that makes all the units work together perfectly. Its value changes depending on the units you're using. But this one you see here, that's the one you'll run into most often in chemistry.
Now, knowing the equation is one thing, but its real power is in using it to compute stuff, to actually predict the properties of gases. So let's work through a real example.
All right, here's our problem. We want to know the volume of 655 grams of methane. We know it's at 25 degrees Celsius and a pressure of 745 torr.
We have 3 knowns and 1 unknown. This is a perfect job for the ideal gas law.
Okay, the first and most critical step before you even touch the equation is to get your units right. That ideal gas constant R is the boss, and it dictates the units for everything else. That means we have to convert our grams of methane to moles, our Celsius temperature to Kelvin, and our pressure in torr into atmospheres. I'm telling you, getting this step right is half the battle.
Next, we just need a tiny bit of algebra. Since we're trying to find volume, or V, we just rearrange the equation to get V by itself on one side. That gives us V equals nRT divided by P.
And when we plug in all our newly converted numbers, we find that 655 grams of methane under these conditions would take up a whopping 1,020 liters. And that just brilliantly shows you the predictive power of this incredible equation.
So let's just pull back for a second and appreciate what this means. We haven't just solved a problem. We've used a single law that actually contains all those other simple laws right inside of it.
Look at this. If you take the ideal gas law, PV equals nRT, and you just hold the amount, N, and the temperature, T, constant, what are you left with? PV equals a constant. That's Boyle's law. Okay, now try holding N and P constant. You get V over T equals a constant. That's Charles's law. See? They all come from this one single place.
And that leads us to our final thought. There's a reason it's called the ideal gas law. It works by assuming that gas particles themselves have no volume and that they don't attract or repel each other. Now, in most everyday situations, that's a great assumption. But in the real world, at super high pressures or extremely low temperatures, those assumptions start to break down. So the question is, what happens then when gases stop behaving so ideally? Well, that is a story for another explainer.